Welcome to this new episode of Meet the Magicians. Today we are going to provide you with a very new result. But we are under embargo. That means that before 11 Central European summertime, we cannot disclose the result entirely. So we will just stay together and chat a bit with one of our magicians, which is strongly involved in this new result. And then at 11, finally, we will be able to reveal this incredible result. So I will just remind you very quickly what is magic, because this weird name, of course, stays for something. The magic collaboration this name stays for Major Atmospheric Gamma Ray Imaging Cherenkov Telescope. This is a very famous image of our telescope, which was taken by our friend Daniel Lovitz, which is an astrophotographer, very famous, and he works for the IAC, the Institute of Astrophysics of Canary Island. So you can see here our beautiful telescopes. They are very special because they don't observe photons, light in the optical range like many telescopes that you probably know about, like classical telescopes, but we detect the Cherenkov light, which is emitted by particles which are produced by gamma rays in the atmosphere. So, okay, it's not a direct observation, but it can give us very important information of the most violent and extreme processes in our universe. And since today, and this entire week is dedicated to black holes, today we will focus on them. NASA prepared a very interesting material about black holes, and this new result, which we are going to announce, is about a very famous black hole. But now I will stop to speak. You know, you can ask a question anytime in our chat, and I will introduce you to two of our magicians, which are very expert in this black hole and in other black holes. So first, let me introduce Alexander. Hello, Alexander.
Hello, everyone. Yeah, thanks for inviting me, Marina.
We are so happy to have you here because you are a corresponding author that in our community means, a very important person of this new result. But there is another amazing researcher which is here. She is part not of this precise result, okay, she's part also of that, but she's also an old friend of this black hole that we will talk about after the embargo. And we are so happy to have her here because it's difficult for her to participate because she's in a very special moment of her life and career. Welcome, Cornelia.
Hello, can you hear me?
Yes, Cornelia. How are you doing?
I'm fine. I'm better than Cleo is doing. Thank you. She's sleeping right now.
Okay, so we have Cleo sleeping. We cannot see her.
Well,
I would like to see her. Yes, it's better not to wake her. So you can imagine Cleo is the new entry in Cornelia's family, and she is sleeping, and we are very happy she's sleeping right now. Okay, now guys, while we are waiting for this embargo to be released, let's tell to our followers something general about black holes. So I will start from Alexander, okay? Alexander, okay, the stage is yours. Can you hear me still?
Yeah, sure.
Fantastic. So Alexander, please give us a very short summary about what a black hole is.
So a black hole is a region in space-time predicted by general relativity, where the gravity is so strong that everything has to fall into a singularity and nothing, not even light, can escape from it.
Okay, well, yes, this is a very nice explanation. I see this little black hole here is rolling his eyes. This is one of the, exactly, that one. The black hole as a singularity is a very complicated object, right? And it's very difficult to observe it.
Yeah, because they don't emit anything. It's a black hole. It's hard to detect. So what we see is either we see matter that's shortly before it falls into the black hole, before it's sucked in, or matter that's in a so-called jet, which is ejected from the black hole. But the black hole itself we cannot observe.
Yes, sure. Maybe we can show again this very famous image of a black hole, and at the same time we can make some consideration about it. So here we have at the center of this image, which I'm sharing, the super famous image which was taken 2 years ago with the Event Horizon Telescope. Everybody is familiar with this image, right? Were you excited, Cornelia and Alexander, when this image was disclosed for the first time?
Well, I actually was, yes, I was, because, M87 has been observed for so many years now in different wavelengths, and covering, detecting or imaging finally, at least in radio, the size of the black hole was quite satisfying. And I also got some feedback from my non-scientific friends who were like, "Oh, I heard about the first black hole image. Can you tell me more about it?" So it was not only an impact on the scientist community, but also in general life. I think some people really got to hear about a black hole.
Yes, some people, they were a bit unhappy, like, come on, all these scientists, and then this black hole is so blurry. But okay, actually, for us, this is the opposite of blurry. For us, this is a brilliant picture with the super resolution. And the Event Horizon Telescope, which is working in radio, in the radio band, was able to do this fantastic job. So for us researchers, this is amazing, of course. And you can see in this visual here how this black hole is inserted in this bigger picture in the left. What is that? I would say this is a representation of an active galactic nucleus, right? Alexander, do you want to tell us something about these incredible objects? And Cornelia, also you, of course, you are both experts. Maybe now Alexander can start.
So the active galactic nucleus is an active black hole. So most of the galaxies we know have a supermassive black hole in the center, and supermassive means that it contains million times more the mass than our sun, and the galaxy is rotating around it, and closer to it, we have the so-called accretion disk, which you can see labeled in the image. And this accretion disk is consisting of gas and dust, which spirals around the black hole until ultimately it falls into the black hole.
Yes, and what is impressive is that in some active galactic nuclei, there is also this jet, those jets, because they are developing in opposite directions. They appear in the vicinity of the black hole, and then they are directed outwards. And in some galaxies, we can observe those jets, and this is simply incredible to see how this black hole okay, we cannot see the black hole, but we can observe with different telescopes this accretion disk and the jets. Right, Cornelia, you observed, you were part of this, of several papers in Magic, but one was about this very same black hole, M87, and you analyzed the data from 2012 to 2015 for this paper, which was published in 2020, very recently. And there, I remember that you did an image in which you put the magic sky map on top of the radio sky map.
Yes, I did indeed. So yeah, the idea was to see whether we can actually localize where the gamma ray emission comes from, and therefore I produced a very high energy sky map, which is quite blurry with respect to the with respect to the radio image, which has better resolution, yet not as good as the EHT managed to have the sky map. And what I put on top were the radio counters, which actually show the outflow of the radio emission in the jets. And there was quite some vicinity between the localization of the source emission in very high energy scene and the center of which is seen in the radio image. However, the resolution was not as good, so it's just you can make a guess that it's very close to the center of the black hole where the very high energy emission comes from.
Yes, I want to share this image because I know that, okay, a lot of people can say, "Boh, we don't say anything here," but we can explain what we see, right? So I will share now this. I will try, okay, because it's in my browser. Okay. I hope you can see it. Can you see this image right now?
Yes, but I think
Okay.
if you can enlarge it a bit more, then it's better.
Yes, I will. Okay, so this image for some people could look like a strange potato, but if you look carefully, you can see below the radio shape, like this galaxy M87 has some patterns around. You can see these jets here in the radio image. Instead, for Magic, Veritas, and Hess, you cannot appreciate all these changes in the jets and around the black hole. You can only study the distribution of the gamma rays in this central region. So, okay, this shows a bit that the resolution of Cherenkov telescopes is not that great, but I mean, it's okay because different instruments can tell us different information, right? So every information that we can get in different wavelengths is useful to understand what is happening in this incredible, interesting galaxy. Okay, so far we spoke about M87, and now there is 1 minute before the embargo is released. But I wanted to show you something and to discuss a little bit more about the multi-wavelength effort. What multi-wavelength means, Alexander?
So, as you said, we need to study a source in all different wavebands with many different instruments to understand all the features and on different scales, the source. And multi-wavelengths means just that we combine all different instruments to better understand the source into one picture.
Exactly. I want to share now this. What is this, Cornelia?
I remember back at the Extreme Blazer conference back in 2019 January, someone said it's like the double bump of a camel. You remember that?
Yes.
The spectral energy distribution, meaning you have the flux of the emission seen from radio up to our energies, which is TeV energies. So you can actually put together the emission you observed in different wavelengths to have this broadband spectral energy distribution. And then you try to connect whether the flux seen in different wavelength bands comes from the same region, yes or not. And if it's so, then you can apply a model and model how these two emissions are related to each other, time-wise
Yes.
and space-wise.
Yes, this shape, which looks like the camel, yes. This shape is super important because if you put together all this information, you have the fingerprint of each blazar. When a blazar is an active galactic nucleus with the jets pointed toward the observer. So we can observe those jets and we can get a shape like this. Okay, but now it's 11 and the embargo is released and this new result can finally be public. So this new result is again about M87. So actually we started to speak about it. Well, why M87? Because it's the closest black hole that we can observe. So to start with it, I would send around. Okay, here you can see the citation of the paper, which is rolling. The black hole, yes, close to Alexander. And now I would like to show this video.
Maybe we can explain very briefly why M87 is interesting compared to blazars.
Of course, and then we go with the video. Of course, Alexander.
Because in the last live stream, Magic covered blazars, where you look into the jet, which is coming from the black hole. And in case of M87, it's called a radio galaxy. So we know many of these AGN sources, active galactic nuclei sources, which emit this jet, but almost all of them, we look into the jet, and that's why we can see them, because then due to relativistic effects, the brightness gets enhanced a lot, and you heard about this in the last live stream. And so we only know 3 where we don't look into this jet, but we see the jet slightly angled from the side, and that's the case for M87. And this enables us to better resolve what's happening and where in the jet, because we can see it from the sides. It's not just all stacked up and we have to resolve it while we look through the different layers, but we can see it from the side, and that's the special thing about M87 and why we love it so much. And luckily it's also very close, so we can see it.
Yes, it's vicinity, but as you said, it's also the configuration. And sometimes it's a bit frustrating because in radio, they can see all these jets developing, and with Cherenkov telescopes, no. But okay, we can provide other kind of information. So, okay, now we show this video, which is part of the official press release. And you will see that with us, we can comment, Alexander or Cornelia, if you want. Okay, so let's go with this video, which is prepared by the Event Horizon Telescope, which is leading this scientific result.
So this is, of course, the very famous picture published by the Event Horizon Telescope, which is the closest we ever got to the black hole. And now we zoom out using different instruments. We are still looking at radio wavelengths. So this is also very long baseline interferometry pictures. And we see more and more of the jet. We see different features in the jet, and we can learn about things going on and where the jet is brighter and how it's likely rotating and some other features. And now we have 3. We have on the left side, we still have radio images. In the center, we have visible from Hubble Space Telescope. And on the right-hand side, we have X-ray images. And we saw the jet in different features. It looks always remarkably similar across the wavebands. And now we've reached gamma rays. And so now this is from the Fermi satellite. And now on the right-hand side, you could see the image composed by Hess, Magic, and Veritas. We are all imaging Cherenkov telescopes, and we were strongly collaborating to produce the result published in this paper. And yeah, but our sky map looks like a space potato, as you called it.
Yes, exactly. There is in this NASA material for the Black Hole Week, there is also a space potato, but I forgot to upload it here. Okay, but you can see it later in some other visual we will make. Okay, so this video is really impressive, but maybe I can share just one picture from this paper so we can have a look at it all together, okay? So also this image is part of the press release of this embargo that finished just a few minutes ago. So you are looking at this picture really, I mean, you are one of the first ones that are looking to this picture. Now we have all these different sky maps from different telescopes all together. Okay, so what was Alexander saying about during the video? We can see now all those images together. So this is, I mean, of course, very impressive. You can see at the left side of this image, in this orange palette, you can see different images in radio. So starting with the famous black hole images, you have other observatories that can observe in radio, as Alexander was mentioning. And then in the center, you have optical and X-ray telescopes. And at the right of this image, we have Chandra, which is X-ray, Mustar, which is hard X-rays, and then this potato here is as Magic and Veritas. And then we have Fermilat, right? So why this image is so important? Because it collects together all the work of these different observatories, right? And this paper that we are announcing is about that. So maybe we can look together to the paper, right? And Alexander, that you were corresponding author of this paper, you can tell us something more about this paper and what you think are the most important results. Okay, and then after also Cornelia, who was part. Actually, Cornelia, this is very interesting because you were part of this work from different sides, right? You were in different collaboration during while this work was going on. But okay,
yes.
Yeah.
The first, I did the analysis of the Mjd data in 2017, and Alexander and I, we were working together to get the data blessed, being approved, being the right analysis. And then in the meantime, I was working in Hess for 3 years. And so I did the Hess side as well. So I worked, yes, on both sides, Hess and Magic on the analysis.
Yes, this is this is something that happens to researchers, okay? Okay, so we were saying we can have a look to the paper and we can check with you, Alexander and Cornelia, which are the most important results, of course. So here we can see this paper. Now the link that we sent for the paper in our social media is active because the embargo is finished. So everybody can look at this paper now in the journal page. But we can show you here this version live for everybody. So one first thing that you can note here on top is that who is leading this effort is the Event Horizon Telescope collaboration. And they are very expert in black hole also, right? They did this first incredible image of M87, and so they led also this work. But they are not the only one involved. Look how many telescopes are working to provide this incredible paper. We have Fermi, we have Hess, Magic, Veritas, this important collaboration EAVN, I hope I'm pronouncing it well, and then so many other people, which they are so many that they are listed at the end of the paper. So there are many, look how many authors and affiliations. Why we need so many people?
It's 760 people involved from 200 different institutions in 32 countries. It's a huge community that had to come together to produce this result.
Maybe some people is asking why so many. Alexander, what is your answer to that?
Well, for big experiments, nowadays, you need big collaborations to run and operate them. First, they are expensive and they need to be maintained. And in case of Cherenkov telescopes like Magic, Hess, and Veritas, we also take our own data or someone else's data. So as a student and postdoc, you have the chance to go to your telescope for a month or a couple of weeks and work there during the night and observe with the telescopes.
Yes, so there are a lot of people involved in making all these observatories work in all the wavelengths. And now, Alexander, in your opinion, because here I'm scrolling, at the beginning of this paper, we have all the description of the analysis.
Stop here. Yeah, the figure one, figure one. That's maybe already the first. It's not really a result, but it shows the effort we have to do. So this is one color for each of the instruments. So in total, there were 19 different instruments involved. And this shows just the blocks when each of the instruments was observing. And it just shows right away, start of the paper, this effort in scheduling, but also for each of the instruments, scientists had to write a dedicated proposal. And in the beginning, it was not clear that we can measure it or that the result by event horizon was that amazing. So everyone had to propose to observe the source at the same time, hoping that it leads to some useful output in the end.
High risk, high gain.
Yes.
Yes, and guys, somebody can ask why Fermi has this huge blue line here. And also somebody...
It observes the sky all the time. It's a survey mode. It's not just a pointing mode. So therefore you have data available at a
Exactly. Fermi is... the Fermi Large Area Telescope is orbiting, so they can make surveys of the sky, and they can, and in this case, they can observe all the time, we can say. Okay, so this is why this line is continuous. And what is MJD? I remember when I joined the astrophysics community and I saw this MJD, I was like, what? So you can tell our followers what it is, right? No, you don't want?
MJD is modified Julian date. It's just a convention to enumerate the days starting from a certain day. And it makes calculating things a lot easier, and also the coordination between the telescopes a lot easier, because when everyone uses the same system, you don't care about time zones or daylight saving shifts or something. You always refer to MJD, and it always switches to the next integer number in UTC time. So it's very convenient, and you get used to it very fast.
Yes, of course. Different communities, they use different units. So there is Julian date, modified Julian date. But okay, in this case, we can just tell our followers that in this Mjd, we intend a unit of time. And in the upper part of this image, you can see the correspondent like human time description, like 57863 is April 20, okay?
But you can think of it like the Stardate in Star Trek they use. It's a number and then some decimal places to give the time during the day.
I like this. Okay. And so scrolling around this very interesting paper, there are, of course, a lot of discussions about this data set that was observed. But Alexander, can you summarize for us what, in your opinion, is the most important result that we can learn for this joint observation of M87 with so many different telescopes?
So then you need to go much further back. So here we describe all the instruments and how we analyzed the data, what were the difficulties, how we took into account the host galaxy, for example. So this now here is already a plot just for the section of our energy band of Cherenkov telescopes. We have combined here the data from Hess, Magic, and Veritas, and the 2 pages
yes,
of
just tell me where do you want the
SED of the Cherenkov telescopes you just showed. Now it's 5 pages back down. The one which yes, this one. And yeah, here you can see that we and our colleagues with similar instruments we observed, and we produced a spectrum in our part of the energy range. And what we saw here is that it's in what we call quiescent state. So it was very silent, and there was no extraordinary emission. It was just emitting, in our resolution, emitting at a very steady state, those gamma rays. And yeah, maybe we can continue to the first one with the modeling. Yeah, this picture we already saw.
Yes, I think the most important result is again the modeling, right, Alexander?
Yeah, well, maybe we can stop here shortly because this one has the labels. So as we already said, is when you observe at different wavelengths in astronomy, you basically directly observe different scales at which this light is produced. And this is very crucial in this case because we observe the space potato. So our resolution is not as good as the radio, which is given by the way how our telescopes work, the method of detection, not because we built a bad telescope. And radio works completely different. They have way more photons they can detect, so this always envies us in the gamma rays. But also there you can see in the different labels, you can see that very different scales are observed, and that the flux point you get is from a completely different region. And all this has to be taken into account when you start modeling, so describing your source and trying from the model to draw some conclusions. And maybe now we can move to the first model.
Yes, sure.
Down, please.
Yes, just 1 second. I have lost the window. I will find it. Yes. Okay. So now I go to the modeling image like this one. Okay.
Yes.
Do you want to? Okay. I will enlarge it a bit. We can recognize a bit the camel. Can we?
Exactly, that's the point where we showed it before, because we want to model this two-humped structure describing different parts of the emission, the thermal emission at lower energies and the inverse Compton emission at higher energies. The camel here is not very visible because with all the constraints we have from the different scales and also other constraints we know from the radio observations, when we all put those in, it's not possible to produce or to describe the radio emission simultaneously to the gamma ray emission with just one emitting zone. And this is what those two model curves show here. And there's another one back down where we do the opposite, where we describe the gamma ray emission, and we can see that we cannot reach the radio fluxes.
Meaning, therefore, that the radio emission and the very energy emission cannot come from the same region. And
exactly. So we need some structured jet. Either we have some different features along the jet, or this structure is in radial direction in the jet somewhere. This needs to differ. And in this publication, we conclude that the quiescent gamma ray emission does not come from the same region where this famous event horizon picture is produced, but it comes further out, and we can conclude that it's somewhere between the black hole and not HST1, which is a feature discovered by the Hubble Space Telescope and monitored for many, many years now.
But yet it's still very close to the base of the black hole.
Yes. But what we don't know yet is where so-called flares. So sometimes we see an increase in flux, and we don't know exactly what causes them. And in the past, we saw them correlated with different kinds of emission, and we thought, okay, now we know it's coming. We know it's produced in the center. And the next time we saw it further out, and we thought, okay, it's produced in this not HST1. So there is not yet a firm conclusion, and we can also not draw one from this paper because it was quiet during this observation period. But that's actually a good sign for the event horizon observations. For their image, they stack, for this famous picture, they stack all the observations, and that we can show that it was quiet all the time during this observation. It validates kind of the way to stack all the images into one. So there was also a recent publication 2 weeks ago or so, the polarization paper, also measured by Event Horizon, where they see that there is some time evolution happening. And that's, of course, very interesting. And also for this, we need to continue observing with all the different instruments. So to study the time evolution of all of this, because this is just a snapshot during a couple of weeks or days, what's happening there at the source.
Yes, sorry, I disappeared, and I have to admit that there is a reason why I disappeared, is because I uploaded the space potato and my computer went completely crazy. But okay, so now we have the space potato that NASA Universe organized for this Black Hole Week campaign.
We can use the Lego magic to observe the space potato.
Yes, you have the Lego magic to observe the space potato. Fantastic. We have another question. Could you somehow profit from the comparison with the Hess and Veritas for the particular source? I can answer, but you answer, okay? Who wants to answer? Cornelia.
Well, it's very difficult to compare different instruments in a very high energy regime, because we are subject to some systematics and uncertainties which come from the fact that you cannot calibrate perfectly your telescope. You rely on simulations and then you make some assumptions. So therefore you have no direct feedback how good your estimate of your calibration, how good your system is calibrated in the end. So you suffer from systematics, and comparing systematics is also very, very difficult between the different instruments. So the only thing I think we learned from comparing the observations is that that we can confirm the low energy, the quiescent state, the low emission of the source during this period. Improving the systematics, I don't think so. Alex, did we?
Yes, systematics is maybe a difficult topic, and it quickly becomes a political topic. Mm-hmm. But maybe one of the obvious reasons is also that our telescopes are collected at different sites. So MAGIC is in La Palma, as you know, and then there's Hess in Namibia, which is even southern hemisphere, and there's Veritas in America. And so when one site has bad weather, for example, the others can take over. So we can get a much better coverage of the stories, and we don't depend on the weather on one location. And this is also part of the scheduling effort, that we always check the weather at different sites and try to shift around when. So of course we have a predefined schedule, and then let's say there are clouds at the magic site, and we can say, okay, can maybe Veritas take over observations of today, and then we try to shuffle them around to get the best possible coverage. And that's helping with the light curve, for example, which is also in the paper.
To have a continuous sampling, yes. However, you rely then on the fact that within the systematics, you measure the same flux. So it's kind of also a cross-check, kind of. If you measure similar fluxes, then you actually save that.
Of course, I mean, there are also different ways to cross-check. We could use a known other source to cross-calibrate. Crab Nebula is the standard candle, and then Cherenkov telescopes, and we can, of course, use Crab Nebula observations to try to match and estimate the systematics, but usually our nightly error bars are anyway very large. I mean, maybe you can show the light curve in the paper?
Oh, yes.
Having large error bars is also due to the fact that we did not observe for a very, very long time during each night. We had 20 minutes observations or 1 hour, depending, right? Depending on the system. So
for magic, it was longer. We observed more than an hour, and in some cases, this was really some key campaign. It was further down.
Bars, because there were less observations during the night.
Okay, let me find. There is an echo. Let me find these light curves. They are divided. Which one do you want to see?
Good. Further down.
Yeah, it must be in the very high energy section.
Yes. No.
This is Swift.
Yes, this one.
Okay. Yes, I wanted also to add. I wanted also. I don't know where this echo is coming from. I hope you can hear me well. I wanted also to add that even if it's very difficult to use Magic, Veritas and Hess data together, there are a lot of efforts in this direction. Also, to study dark matter, we are combining results from different facilities, from Magic, Hess and Veritas. For instance, there is a project, the GloryDuck project, which is working on this. So we want to combine data from Magic, Hess and Veritas, and we are working a lot in this direction, even if as Cornelia says, and she knows because she worked in all this collaboration, even if it's not easy. So, okay, I will enlarge these light curves so we can see them better. Okay, like this.
Yeah, it's not very special, so it's compatible with constant flux for all instruments. But what you can see is that Magic dedicated a lot of observing time during this campaign. So Magic observed for more than 27 hours the source to get also the nice points in the spectral energy distribution. In between, you see a big hole surrounded by data points with large error bars, which is where we cannot observe because of the full moon. So we have to shut down the telescopes, and when there is a moonlight during our observations, also our sensitivity degrades. That's why the first error data point afterwards has so large error bars.
Yes, and since I think I remember Magic can still observe during moderate moonlight, while Hess did not. So therefore, you have even more coverage from Magic than from Hess. But
for this campaign. For this campaign, I think we got 2 nights more than Hess and Veritas, I believe.
I think then Hess had a lot of problems with bad weather because it's in April and then you have...
Yes, we cannot control the weather yet.
Which is different at different sites and different periods.
Yeah, it's sometimes it's very hard. Okay, so I think we answered to this question, and even if we gave 3 different points of view, well, this is because it's not it's not easy to combine data from different observatories, but you know that in the near future we are creating a facility, the Cherenkov telescope array, and in this huge observatory there will be a lot of Cherenkov telescopes, and this huge effort is made combining people from MAGIC, Hess and Veritas. So we are combining not only results but also people, and this Cherenkov telescope array will use software which you know will put together different experience of people which are working in with very different software and analysis right now. Okay, so do we have another question, or maybe I don't know, we can say something just to conclude the event? How is the situation from the backstage about questions? Maybe we don't have questions, okay? Well, this is normal because we were announcing a new result and people take some time to digest it. So I would say there is something that you want to add, something that you think our followers need to know about this new result.
Well, one thing which is, I mean, we talked about the spectral energy distribution and how it's nice, and we expect that many theorists and other experimental physicists will use it to describe sources and similar sources. But maybe what we did not talk yet about is what we learned by combining all those different scales, that we do not necessarily expect the model to fit all data points because we have to respect so many different boundary conditions we learn from all the different wavebands, that also for other sources, for example, where we look into the jet displacers, maybe that our paper here for this radio galaxy can also give important inputs for describing blazars as well.
Okay, yes, this is also very important and interesting. So we will keep observing this incredible black hole in different wavelengths with different telescopes, and we are very happy that MAGIC is part of this effort. So Cornelia left, but she came back with a surprise. Hello, Cleo, you are so beautiful. Ciao.
You made it through the entire session. Yay!
Oh, yeah, bravissima, Cleo. Sorry. This is fantastic. So I think this is a perfect closure for our event. Hey, Cleo. So yes, this is life of researcher, right, Cornelia?
Yes, especially during COVID.
We are very happy to have meet also Cleo today, and I want to thank you all so much for being here with us and disclose for the first time to our followers this new very important result. Please send us any question you may have, and we will reply to you soon. Thank you so much again. Bye, guys.
Thanks for having us. Bye.
Thanks.
Bye. Ciao.
Bye.
Ciao, mamma.